So today we are starting our fourth unit of this class, which is all things polynomials and quadratics. And these are terms that we'll cover in more detail later. But what we use a lot of to accomplish these tasks has to do with exponents. Sorry. So exponents we probably recall those from our order of operations. They were the E and PEMDAS. And you've probably, again, depending if you came from math A or B, you probably did some work with exponents there as well. But those were typically done in just expressions. You evaluated them. You probably didn't dive into detail into what they exactly do or how they can be utilized, or there's actually a whole set of rules that they must follow that allow us to manipulate expressions that contain all sorts of exponents. So we're actually going to dive into it today. Quick warning in advance. This is one of my lesser favorite lessons, solely because when we cover these topics by themselves, it almost seems chaotic. Because what we're left with doesn't feel any more useful than what we start with. Because all we're doing today is running through exercises on how we can combine things involving exponents that have pieces in common. So it's not going to feel like we're attaining much today, and the assignment kind of feels the same way, but I promise you the skills we pick up here in this lesson will help us immensely in tomorrow's lesson and several of the lessons next week. It's going to make us a lot more comfortable in manipulating problems to fit our individual needs. Because if you think about it, pretty much everything that we do, if you were to oversimplify Algebra 1, it's all about solving equations. And every equation is unique. We've spent a majority of our time solving what are called linear equations. Now, some of those equations had one variable, in which case we got that variable by itself. If it had two variables, typically we would imagine it as a line, all the points along that line being solutions. And then we even threw in systems of equations where we considered two or more lines, how they interacted with each other, what they had in common, and so on. But everything we've done so far has been linear, and we haven't seen any exponents since day one, where we briefly used them in order of operations. Everything we do from this point forward, exponents are going to be along with us the entire way. So first thing we're going to do here is going to use this little quick diagram to label some of the pieces, put a couple notes. This is going to be the vocabulary we use throughout our next few lessons going forward. So first off, most people, if you ask them what an exponent is, they will describe it as that little number that's kind of floating next to a larger number in terms of actual physical size. So in this little diagram here, that exponent would be represented by the letter M here. Oh no, my pen lost connection. So this would be the exponent. Now what you may sometimes hear me refer to it as also is a power. And I typically use those words interchangeably. They are describing the same piece, which is the exponent. But depending on where you're reading it, the context you're reading it in, it may also be referred to as a power. Now, the thing about exponents, they cannot exist by themselves. Every exponent must be attached to a larger written piece or value, and that is called its base. So off to the right here, a couple comments that I'm going to write down. Every base has an exponent. And the second thing that's true is that every exponent must have a base. Now, some of you may be saying, well, if every base has an exponent, we've been seeing lots of numbers so far, and we didn't see any exponents on there. If you were to guess, if you don't see an exponent, do you know what that exponent actually is?
1.
It's a 1. And similar to coefficients, exponents of 1, because they don't really alter anything, typically like to hide. Same as our coefficients of 1. Well, when you multiply by 1, nothing changes, which is why we usually hide them as well. So even though we haven't seen exponents for weeks now, they've actually been there the whole time. They've just been exponents of 1, and they've been hiding from view. Now, sometimes we'll come across more exponents of 1, but we're more interested in all the other exponents out there. So the next statement here says that exponents describe how many times a particular base is being multiplied with itself. So that's really just kind of an informal definition of what exponents do or allow us to do. And again, we're going to start off with kind of an area where we're more comfortable. We're going to look at exponents that belong to bases that are numbers or values. If a base is a value, we can actually evaluate it, meaning find the actual total by utilizing that exponent. So for the first couple here, I'm going to show you what it looks like longhand is what I like to call it. I don't know if that's the official term, but it basically represents what that exponent is telling me to do. So for these first two examples, I have 3 with an exponent of 4. If you were to describe, I don't need the answer. If you were to describe your process to evaluate 3 to a power of 4, what would you do?
Multiply 3 by itself 4 times.
Multiply 3 by itself 4 times. So if I needed to see that, would it look something like this? 3 times 3 times 3 times 3?
Yes.
So notice it's the same value, the base, which is 3, and the number of times I write it down multiplied together is determined by the exponent. That's it. Exponents are just shorthand ways to show this rather long bit of multiplication, because now, even without a calculator, I could go back and I could one pair at a time multiply them. So 3 times 3 would give me 9. 9 times 3 would give me 27. And 27 times 3, I believe, gives me 81.
I do mine different. I take 3 times 3, then 3 times 3, and then I take the number.
The 9 times 9, that's fine. So there are different varieties here depending on how you multiply them together. But so long as you multiply everything together through that process, you should still reach the same conclusion. Now, Toby, I didn't miss what you said. You said you got 12.
Yeah.
And that is probably the most common mistake, because what did you do?
I multiplied 3 times 4.
You did 3 times 4. So this is where some of the confusion comes in. We use multiplication when dealing with exponents, but that doesn't mean that we multiply the base with the exponent. So if anytime I'm dealing with exponents, that is by far the most common mistake I stumble across, is that students will take the base, whatever value it is, and multiply it just directly with the exponent. That is not quite what we want to see. Now, the next one, again, relatively simple. What is 5 to the power of 2? What is it essentially telling us to do? 5 times 5. So 5 multiplied with itself 2 times. So 5 times 5 would give me 25. Now, so far, these two examples weren't too big of a lift for us to work them out by hand. Now, imagine if the base or the exponent started to grow on us, which inevitably is going to happen. And we consider our third example here, which is 12 to the power of 5. Well, if I wrote it out, it'd be 12 times 12 times 12 times 12 times 12. Well, already 12 times 12 is 144, and the next multiplication will grow even bigger and bigger and bigger. Writing it out longhand is not always going to be practical. So it's at this point, I usually recommend that either if it's on your phone or if you have access to a scientific calculator, this is usually my little shameless plug of saying, go to the store. Usually for less than $10, you can find a decent scientific calculator nowadays, and it'll allow you to do exponents significantly faster. The hard part is finding the button, because for whatever reason, the calculator manufacturers of the world have not agreed upon the same format. So what I usually do at this point is I list some of the ones that I have stumbled across myself. So these are possible calculator buttons that you may stumble across when trying to do an exponent. The one I've seen most frequently uses the caret symbol. Often we see this in English class to insert a word between two other words, but in math class, that symbol says that whatever value you entered first is going to be raised to a power of whatever value you enter second. Now, there are even more advanced calculators out there that actually go a little bit further, and they look a little bit cooler. You may see something like a base x raised to a power of y. You may see, so you don't want e to the x. That is something different. That'll be something that you'll cover in Algebra 2. Uses exponents, but very unique situation. You may come across x to the power of a little box. Or I've even seen some where it's a box raised to another box. And like I said, it really just depends on the brand of calculator you've purchased. And even such, some of the same brands out there, depending on which model type you're using, there's even differences between those as well. So this isn't an all-inclusive list. There are other ones out there. Sometimes I've seen, instead of X and Y, I've seen A's and B's or M's and N's. Sometimes I see the X and Y's switch positions. The list could go on. It's what we need them for. That's what they all have in common. So here's what I usually do. This is just a personal recommendation. Of course, I'm always full of recommendations. Is anytime you're working with a new calculator, one that you may not have used before, and you need to use it to calculate or evaluate an exponent problem, do one that you already know the answer to. So for example, my go-to is always 5 to the power of 2, sometimes referred to as 5 squared. So I grab this new calculator, find the button that I think does the exponent, and I type in there 5 to the power of 2, or at least the way I think the calculator wants it. And when I hit equals or enter or whatever the button says, I know it should be 25. And if I get anything other than 25, I know that 1, I've either used the wrong button, or 2, this happens sometimes. Typically, I found it on cell phone calculator apps. Sometimes there are ones out there that actually want you to enter in the exponent followed by the base. Now, to me, that feels very backwards. Some may argue, but until you know how your particular device, whether it's on your phone as an app or whether it's an actual calculator, until you know what the button and the functionality of that is and how it works, test it out on ones that you already know the answer to. I like to use 5 to the power of 2. So real quick, I'm going to pause for like just a minute or so, not a minute, a few seconds. If you have a calculator nearby, or if it's on your phone, try it out real quick. Try 5 to the power of 2. You should get 25, because if you can get 25,
I have 3 different exponent buttons though on my phone.
well, there are,
I have X to 2, X to 3, X to Y.
you want X, well, technically the X to 2 would work there, but you want X to the Y, because then you can choose the base and the exponent. So again, there are so many varieties out there, it's almost impossible for me to consider every single one. But try it out real quick. Toby, did you get 25? You got 25? Leanna, how's yours? 25? Hopefully you guys online, if you run into any issues, let me know. But hopefully with whatever device you're using, you can get 25 as well when you take 5 to the power of 2. Once you feel comfortable with your device, try it again and evaluate for me 12 to the power of 5.
Do you want the answer?
Yeah, if you don't mind.
248,832.
248,832, you said?
Yes.
And if someone else wants to fact check, again, just a good exercise to practice.
I got the same thing.
You got the same thing, Leanna?
That's what I got.
That's what,
Yep.
Good. So it sounds like you guys
That's
found,
what I got too, Josh.
awesome. So it sounds like you guys have found the exponent button and you're using it appropriately. And as you can see with a calculator, what would have taken, maybe a few more steps as we multiply 12 individually over and over and over again, was relatively quick. A few button presses on our calculator or on our phone, and we get a relatively large number.
I didn't use the exponent buttons.
You did not use the exponent button?
No.
You do 12 times 12 times 12 times 12 times 12?
Yeah, I just did it the harder way.
Which is okay. And I won't tell you that you have to do it this way, but here's where I would normally see it come in handy. If I said I need to now know 2 to the power of 53, do you want to sit there and do 2 times 2 times 2 times 2 times 2? And then I say, oh, hey, Alexis, by the way, did you see that show last night? And the next thing you know, crap, I forget how many times I've done it. I've got to start over again. So it will work. It does require a few more button presses. It's not the end of the world. But as those exponents get larger and you have to count them out individually, you are unfortunately opening yourself up to an opportunity of miscounting.
But I did check it with the exponent button to make sure I did it right.
Perfect. All that I ask is you, at the very least, know where that exponent button is, feel comfortable using it. I can't make you use it because there are other ways to do it. I just wanted to make sure that I did my part and said, here's that button, guys. So awesome. So Alexis, however you feel comfortable, I do appreciate though that you went back and did check it. So that's always good news. Now, I bring in the next 2 examples. And a lot of times students say, well, hold on, those look fairly similar. They both seem to have a base of -4. They both seem to have an exponent of 2. And I would say yes. And for the most part, everyone would say, well, I do see that one of them has parentheses and the other one does not. Now, this is a losing battle that I usually experience every term, because some calculators actually calculate this incorrectly. My classroom set, as a matter of fact, they are, I think, Casio's, I forget which model number, will actually give you the same value for both of these, but these are actually calculated with a slight difference. And here's where the confusion comes in. And until someone tells you that this is what's happening, you'd never know to check it. But if you have, I think most Texas Instruments calculators, and I want to say most apps on phones will do this correctly as well. If you enter in these 2 calculations separately, but enter them in exactly as you see them, you should get 2 different results. Should. If you're not, well, then unfortunately yours is on the list of ones that are also fooled by this little math trick. So I'm going to start with the first one, and we're going to see this in longhand version just to see why we get two different results. The first one, what is our exponent? A positive 2. What is our base?
-4.
It looks like a -4. And here's where the trick is. Technically, the base is 4. The negative doesn't have any visual cues technically that tells me that the negative is 100% attached to that 4. And what you can actually rewrite it as is that this is a -1 times 4 to the power of 2.
Have you seen Leah's cheat sheet with this?
Mm-mm.
I'll go ask her for it.
I'll have to see. So apparently Leah has a cheat sheet for this calculation, which is exciting because then it means I'm not the only one who's aware of this
I'll go ask her during the break
frustration.
for us.
Perfect. So what's happening here is, if you recall from earlier lessons, parentheses really serve as our go-to grouping symbols. And that grouping symbol says everything inside is included in the action that we perform. On this first example, technically there is no grouping symbol saying that that negative sign has to belong to the 4. Now, in past lessons, especially when we were solving equations, we usually move them together, and it worked out perfectly fine. But exponents like to kind of step outside the bounds here a little bit on us. Now, if I was to finish calculating this, what is 4 to the power of 2?
16.
16. And if you were to take -1 times 16,
-16.
you would get a -16. Now, if your calculator is in good working condition and it follows the mathematical rules, if you put in -4 to the power of 2, you should get a -16. Does yours?
Oh, yeah.
Yours did it?
Yeah, I did the normal.
Okay. Is yours not doing it?
No, iPhones are stupid.
Your phone's not so it's worth a check, because there are some calculators that will actually miscalculate this. Now, in the grand scheme of things, is it the end of the world? Well, unless you're something like an astronaut or an engineer or something that is super advanced and it requires super precision, you'll probably be okay.
Yeah, I got -16.
You got -16 on yours, Toby.
Yep.
Awesome. What kind of phone are you on?
Samsung.
You're on a Samsung device, so you're using whatever app comes on that. Leanna, you said your iPhone did not do it.
No, it just gave me 16.
Okay, so yours produced +16. So again, it's worth,
Yeah, mine didn't do it either.
so yours gave you a +16 as well, Jay?
Yeah.
Okay, so this is something that does happen. But I'm here to tell you, without the parentheses wrapped around that base, the negative sign is not included with the exponent. Then we transition to this other example that looks similar, but has the parentheses in it. So what this is actually doing is saying that all of that inside the parentheses is our base. And according to exponents, that means that we are taking that base of -4 and multiplying it with itself a total of 2 times. Well, what is -4 times -4? A +16. Now again, for your average Joe, the odds of you even encountering a scenario where the exponents are going to do this weird thing are slim. But if, let's say, you work for a stock brokerage or some sort of financial institution, and they have these really neat formulas that they use to calculate all sorts of measurements and things that deal with money. If this was done incorrectly,
So if it don't have parentheses, then it's -1. And if it does have parentheses, it's -4 to the second power.
yeah, so the parentheses
Okay.
change what the actual base is. So in this case here, without the parentheses, the only base was the 4. With the parentheses, the base is everything inside. So that's the key difference. Now think about it. If I was a financial institution and, you know, is there a big difference between negative $16 and positive $16?
Yeah.
There sure is. It's the difference between having that money and owing that money. So yes, there are scenarios out there where this mistake could be catastrophic, potentially. But like I said, this doesn't come up often. And I don't even think there might be one on the assignment today. But I wouldn't be able to sleep with myself at night if I didn't bring it to people's attention. All right, last one here you'll notice is even more unique than all the others because this one has an exponent as well, but this time the base is no longer a value, it is a variable. So if I was to think about this, you know, write it out longhand, x to the power of 4 technically is x times x times x times x. Here's the problem. What can I do with that?
Nothing.
Why nothing?
Because there's no numerical value.
But X is 1.
Well, we don't know the x is 1. There are ones as coefficients if we wish, but a variable, if you think about a purpose of a variable, it's for values you don't yet know. And if I don't know what x is, do I have anything that I can actually evaluate by multiplying them together?
No.
So variables are going to require us to manipulate the exponents in a different way. Because until you know what x actually is, you really can't go any further with this. In fact, it is common practice to actually leave it written together. Because if you think about it in terms of a workspace on a piece of paper, writing out x times x times x times x is going to take up more space than just leaving it as x to the power of 4. They both represent the same thing. And at this point, if I told you, okay, guys, x is 7, would you rather sit here and do 7 times 7 times 7 times 7? Or would you rather grab your calculator and do 7 to the power of 4? 7 to the power of 4 would certainly require a little bit less work, which means leaving it in this format kind of makes sense. So I'd like to say that most of that was essentially a review with a few hidden surprises in there, things that are often overlooked, and a quick introduction to how to use our calculators, except when it comes to a negative base. That's where we have to kind of stop and make sure we know what our calculators are doing. Otherwise, though, calculators are an amazing tool when dealing with exponents if the base is a value. The base won't always be a value. So this is going to be, so got a question here from Miranda. So is the problem, if the problem is x to the power of 8, would it still be x to the power of 8? Yes, you could write it out as x times itself 8 times, but it wouldn't get you any closer to a solution because there's no value for x yet. So typically we would leave x to the power of 8 as x to the power of 8. Now, unfortunately though, calculators cannot do variables, so we have to learn some other rules that allow us to manipulate these expressions to fit our needs later on. So here's where we start to get into the nitty-gritty. We're going to cover some scenarios that are tied to rules that govern how exponents can be manipulated. And we're going to start with two rather unique scenarios involving negative exponents and exponents that are 0. So we're going to start with negative exponents. I'm going to highlight, we do not like negative exponents. And the reason for that is if you try to think of it quantitatively, based off of what we know exponents do, it really hurts our brain to try to think, how can I count this out -3 times? Or -7 times? So negative exponents really kind of hurt our brain. Now a calculator can evaluate it, but it's going to give you an answer that you may not understand why you're getting that answer. So we're going to dig into negative exponents, and we're going to figure out a way to make these negative exponents positive so we can actually do something with them. So to make a negative exponent positive, switch the exponent and its base to the other side of the fraction. This is just a maneuver. All it changes is the sign of the exponent. So let's see it in action. We're going to rewrite each of these following expressions that all have at least one negative exponent. We're going to rewrite it in such a way that the exponent turns positive. So starting with these first two, I'm going to ask some questions that seem simple, but I need your brain to be in that mind space. So on the first one here, 2x to the power of -3, all of that over 3. Do we have a negative exponent?
Yes.
Yes. What is the base of that negative exponent?
2.
X.
So I heard the 2, I heard the x. On here, Miranda's saying x. Marissa's asking, is it 2x? So that's a good question.
I was gonna say 2x too.
So do you know what we would need in order for that exponent to belong to both the 2 and the x? We would need parentheses. So right now, 2 is actually considered its own base. X is considered its own base. The only base that has the negative exponent, I'll zoom in here so we can see it, is the x. So this this right here is the problem. The 2 actually has its own exponent. We don't see it because it is what?
1.
It is a 1. So it, technically, if I wanted to, oops, it's not what I wanted either. Technically, there's an exponent of 1 on the 2, and there's also an exponent of 1 on the 3. Those are both positive. I'm okay with those. So I'm really just unhappy with the x to the power of -3. And here comes the trick. I need to move that exponent and the base it's attached to the other side of the fraction. Boop. What would that look like? What's left on top?
2.
There's a 2 left on top. What's now on the bottom?
3x. 3 to x, and then the -3x on it.
Well, it wouldn't be negative anymore.
Well, positive 3.
That's it.
So we don't need to solve it?
We can't solve it because of that variable. Also, notice, what do you not see anywhere? These are called expressions, which means they don't have
An equal sign.
an equal sign. And without an equal sign,
It cannot be solved.
it cannot be solved. It can only be simplified or modified. So I got a question here. Why is it not negative? I think I missed something. You didn't actually miss anything. If I was a really cool animator, I would make a little mini video here where as that piece moves from the top to the bottom, it would switch. So let's try my skills here real quick. Let's check this out. I think if I have it handwritten here, I can kind of do a little animation. So all I'm doing is I'm moving this base that has the negative exponent to the bottom, and all that changes, other than the location, is that the exponent turns positive. That's it. In fact, if I were to do the opposite, if I were to move something that had a positive exponent to the other side of the fraction, it would switch its sign again, back to negative.
Why would you put it on the bottom?
To make the exponent positive. That was the only goal. I don't like negative exponents. The only thing that accomplished is that it made the exponent of -3 turn positive. It didn't allow me to solve because I can't solve. It's just an expression. And it didn't allow me to evaluate because I have that variable in there. You can't evaluate without knowing the missing values. So all it did was turn that exponent positive. So you move a base with a negative exponent to the other side, that exponent changes its sign.
So it does nothing to that 3. That 3 is all by itself. Like if that 3 was negative and you're moving the negative down, it's not going to like change it or.
Are you talking about the 3 that was in the denominator originally?
Yes. Yes, sir.
I didn't mess with it because its exponent was a +1. I like positive exponents, even the ones that are hiding. So I didn't need to mess with it. It stayed put. The 2 on top stayed put. Nothing changed with those. The only thing that changed is that base is now on the other side of the fraction, and its exponent went from negative to positive. So we don't keep the x in the first problem. So we are keeping the x in the first problem. That x went from here down to here. This is the same x. All it has done is it's moved from the numerator to the denominator, and that transition changed the negative exponent to a positive exponent. If we did it in reverse, a positive exponent could potentially turn back to a negative exponent, but there's no situation really that we would want to do that because we don't like negative exponents. I hope you see what I'm saying. I hope you're not just making me feel better because I haven't actually explained it any better. Because if I haven't, let me know. Call me out on it. But let me show you. Let me show you at least one more, and let's see if we can start to notice a pattern. I appreciate your honesty, Marissa. Sometimes students just like get so discouraged asking questions, and if I don't do a good enough job re-explaining it, they just go, "Oh, okay, yeah, I got it." They don't got it. But I appreciate your honesty there, Marissa. So thank you. So let's take a look at the second one. Similar scenario, a little bit different. Do we have a negative exponent?
Yes.
What is the negative exponent? -5. What is the base it belongs to?
Y.
The y. The 5 has its own exponent. We just don't see it. So I'm really just concerned about this piece of information right here. How do you make a negative exponent turn positive?
Put it on top on that page.
In this case, put it on top. More generally,
Move it on top.
put it to the other side of the fraction. So in this case, the y to the -5 is going to slide up top. So what's now on top?
Y with the
4y to the positive 5th power.
4y to the positive
How do
5th
you
power.
say that? Like if you're just talking about it, it's like awkward.
How are you?
Not
How
know
would you
how to
just?
say it.
How would you describe this statement? Well, let me finish writing it real quick. So verbally, I would say that this is 4y to the 5th power all over 5.
Okay.
I wouldn't say. So it would get a little bit tricky, and that's where some of the language complicates things, which is why I always recommend writing things down. Because verbally, if I said 4y to the 5th power, am I saying all of 4y is raised to the 5th power, or am I saying only the y is raised to the 5th power? Unless I clarify, you may not know. So the language behind it can complicate things, unfortunately.
I wonder if they took it carrot fed.
You could say care. Yeah, you could use, there's lots of ways you could probably describe it. But if there's ever a miscommunication, a great way to fall back and make sure everyone's on the same page, write it down. Write down what you're trying to describe. Okay. So again, where it starts, where it ends is irrelevant. It's that transition. It's that movement that turns the exponents positive. All the other bases stay put. Now, this third one is a little exercise I like to throw in here just to show you why it's nice to be able to understand what negative exponents they're doing and why it's a little bit harder to calculate if we're doing it by hand. So real quick for me, a little side exercise. In your calculator, put 4 to the power of -3.
Can we put it over 1 and make it a?
We'll do that in just a minute. First, let's just see what the calculator tells us.
First of all, I don't know how to do that on my calculator.
I think on yours, you do the base 4, you do your exponent button, you press 3, but then do the plus minus to make that 3 negative.
0.015625.
0.01.
5625.
5, 6, 2.
And that's not rounding, that's exact, right?
Yeah, that's exact.
Okay, so off to the side here, I'm going to make a little note that according to my calculator, 4 to the power of -3 is this value right here. So that's a bit of a head scratcher at first because so far, all the other exponents, if I look right up above here, all the other exponents seem to do what to my bases?
Actual numbers.
Well, all these are actual numbers, but let me use 12 to the power of 5 as an
It turns to
example.
a whole number.
A whole number, but more specifically, do they get bigger or do they get smaller? Typically, positive exponents make really big numbers. So maybe it kind of makes sense that a negative exponent would have the opposite effect. It makes a really small number. So positive exponents make really big numbers, negative exponents make really small numbers. Slight spoiler alert, depending on which science class you're in, eventually you'll reach a point where you have to work with numbers that are both really big or really small.
Are you talking about ICT?
I'm talking about scientific notation. So if you're measuring the distance between stars, you're talking about really big numbers, and you need a way to write those really big numbers in a small, compact way. Scientific notation with positive exponents allows you to do that. If you're talking about the diameter of an atom, which is significantly small, well, now you need to write a really, really long decimal because really small values are really long decimals, but I need to cram it down into a smaller space using negative exponents. So depending on where you're at in your science lineup, you may have already come across that, you may kind of recall it, or it may be coming down the road. But let me show you why we get this particular value. And it's going to do with the little trick we've been using to make the exponent positive. So Leanna, you were already ahead of me. You said, can we make this look, you said, can we write it over 1? Why would you want to write this over 1?
Because then you can flip it and it'd be 1 over 4 to the positive third power.
Okay, so you said something about flipping it. And if you think about it, so far, everything we've been doing, we've been moving the bases that have negative exponents to the other side of the fraction. Well, this one didn't look like a fraction, but if we go back to our days of slope, any of our slopes that didn't look like fractions, we wrote them over 1. So we apply it here. Well, I take this base and I move it to the bottom. So technically I'm not flipping it, though it looks like I'm about to, because all of a sudden we need to have something left on top, but guess what's been hiding there all along? What's always hiding?
1.
1s. So there's now a 1 on top, and with a base of 4 to the power of positive 3 now because of this switch. Well, 4 to the power of 3, that's something I can evaluate. That's more comfortable. That is 1 over 64. 4 to the power of 4 to the power of 3 is 64. It now happens to be in the denominator, however. Is 1/64 a big number?
Yeah.
Is it?
I mean, it's bigger than 50.
1/64 is bigger than
It's a
50.
fraction.
It is a fraction.
It's a smaller.
It's actually a really small number. If you were to measure something now and you wanted 1/64 of an inch, well, one, that's really hard to see because that is really small. The bigger the denominator of a fraction, the smaller the value actually is. Now watch this trick. Grab your calculator. Do you know how to convert a fraction to a decimal?
Divide the top by the bottom.
Numerator divided by the denominator. Guess what you get?
Mixed number,
Shouldn't.
whatever.
1 divided by 64.
0.015625.
So our calculator knows how to manipulate negative exponents. Our brains think, well, why is it giving me this really long decimal? Well, it's giving me a really long decimal because in changing it to a positive exponent, we're taking what wasn't a fraction and turning it into a fraction. And as that denominator gets larger, the value actually gets smaller. So the calculator knows what it's doing. And everyone says, well, I have a calculator. You don't know what the calculator is telling you or what it's doing or why it's telling you what it's telling you. Yeah, great. The calculator knows, but do you? Alexis, did you have a question? I saw you pop up there real quick.
No, my son was pressing buttons on the
Okay,
computer.
just checking. So negative exponents make really small values. Positive exponents make really large values. In the event that we ever come across a negative exponent, we can know that we can do a little switcheroo and allow us to make the exponents positive. So let's practice with a couple more here. That was kind of a little segue. Maybe I should, I don't know, kind of isolate it from the others. Segue is not the word I wanted. Side note. But it used the same little trick that we've been using for these other ones. Okay. Obviously, I have to pick up the complexity a little bit. And I'll say that the hardest part today is going to be staying organized, because now we have these fractions, we have these bases. Most of these bases now have these little exponents. Some of them may be negative. Organization is going to be extremely necessary to help you not get overwhelmed, because it does seem overwhelming at first. But once you find your groove, you'll be good. On this next one here, any negative exponents?
Yes.
2 of them.
There's 2 of them. What's the first one you see?
X to the negative second power.
X to the negative. So you already kind of answered my next question. So the -2 on top belongs to the base X. So we'll need to address that one. What else do you see?
And to the negative 7.
N to the -7th. So we'll need to address that one as well. Okay. Notice, what did I not touch? The 3 and the 7. I'm not going to mess with those. They stay put. Everything else needs to switch positions. So that means that the n, oh gosh, wrong tool. That means the n to the, excuse me. Feels like a Monday all of a sudden. The x to the -2nd is going to have to move to the bottom, but the n to the -7th is going to move to the top. And when that switcheroo is done, what is now left in the numerator?
3n to the positive
No.
7
3n to the +7th.
over 7x to the positive 2nd.
Good. The 3 and 7 are the same positions they were before. The bases that had negative exponents are now on the opposite side of the fraction bar from where they originally started. And that's it. That's all I can do there. I can't evaluate because I don't know what x is. I don't know what n is. But now the negative exponents are gone. It would make it easier to work with later if I needed to. Okay. Last one here. How many negative exponents do you see?
3.
Okay. Call one out. You can attach the base if you want.
The b to the negative 5.
B to the -5. So that's going to need to be addressed. What else do you see?
C to
A to the second power.
C to the -8. A to the second power actually is good. A to the second power there is already positive. I don't want to mess with it. Because if I actually moved A to the second power to the denominator, do you know what would happen to the exponent?
Negative.
it would turn it negative. That's the opposite of what I want to happen.
Then x to the negative 3.
We also have x to the negative 3. And that appears to be all the bases that have negative exponents. So a to the second is safe, y on the denominator is safe, z to the second on the bottom is safe. So I don't want those to move at all, but I do need to move, did it again, b to the negative 5th to the bottom, as well as c to the negative 8th. But x to the negative 3rd is going to move to the top. So I've got this massive shift happening here. And at this point, students are like, oh my gosh, which order do I write them in? Technically, it doesn't matter, so long as they're on the right side of the fraction. But if you're an oddball like me, I usually write mine alphabetically. So for me, if I was writing this, I would say that the a to the second is still on top. The b moved, the c moved, but the x came up top as well. So I'd have x to the 3rd. On the bottom, again, kind of thinking alphabetically, I see that the b to the negative 5th is now down here, which means it's now b to the positive 5th. C to the negative 8th is now down here, so it's now c to the positive 8th. Y didn't move, neither did z to the power of 2. And that's it. Now this is usually where I get some grumbles because it's like, what did I accomplish? Not much.
So what you're trying to do is take the negatives away from the
Yes,
problem.
that was really our one and only goal. We don't like negative exponents. So with that little maneuver there, we made them all positive. And that's all we did. We didn't get any closer to some sort of solution. We didn't solve or evaluate. And that's okay. That wasn't our goal from the beginning. All we were trying to do here was make those exponents positive, because now if I was to throw this expression into a larger equation, this expression would be a little bit easier to work with. Now that's getting into the advanced side of things, so you won't see that for a long time. But being able to manipulate problems and make them look more favorable is a good skill to have. So we don't like negative exponents, but we do have a way to make them change. So I got a question here. Do you always start with the negative exponents on the top and just move them down to the bottom to make them positive? So it really just depends on where they started. So I know it looks like I focused on the top ones first. It doesn't really matter where you focus. My ultimate goal was to only move bases that had negative exponents. So yes, I did. I focused on the top first, so to speak. And that was just a personal preference. The goal is where they land. That's the important part. Which ones you technically move first doesn't actually matter, so long as you only move the ones that have the negative exponents. So the letter goes with them when you move it. So yes, so as I mentioned up above earlier in the notes, every base has an exponent, but every exponent must have a base. So that exponent cannot move independently by itself. It has to move with the base it's attached to. So they move together as one. And it may not always be a base that's a variable. We saw an example there earlier on where maybe the base is a value. That base still moves with it. Good questions here. Good news, the last little segment on this side of the notes is a little bit easier. And that's about zero exponents. Zero exponents tells me that any base raised to a power of 0 equals 1. Now that's usually mind-boggling for students, but it's kind of fun to see. Based on that statement, what's x to the power of 0?
X
0.
Nope. Any base to a power of 0 equals 1.
1.
123 to the power of 0.
1.
Is 1. X to the power of 0 is 1 times y to the power of 0, which is 1 times z to the power of 0.
1.
1. 1 times 1 times 1
1.
is 1. Next one here, notice the parentheses. So that everything inside is being considered as the base. So 23abc raised to the power of 0.
1.
9,999,999 raised to the power of 0
1.
is 1. I don't care how crazy the base gets. If you can say that that entire base is raised to a power of 0, it equates to 1, which is great because that means we can simplify some pieces, because ones often hide later on in our problem. Now, if you're curious as to why that is, it takes a little bit deeper level of understanding and some imagination. That's something I'd gladly chat with you about later on. But for right now, if you just remember that any base raised to a power of 0 equals 1, you're good. Any guesses what the most common wrong answer is here?
0.
0. Lots of people want to say 0 because, again, their brain goes to multiplication and they think every time I multiply with 0, I get 0. Exponents don't get multiplied. They tell us how many times to multiply. They follow their own rules. All right. So the front half of the notes is kind of abstract, is how I would define it. The second half of the notes is where we get into the more useful rules that we can utilize to simplify rather messy expressions down into something a little bit simpler to use later on. So I'm going to throw out there real quick. Each of these rules actually, they're called properties. Each of these properties have unique names. If you want to learn their names, awesome. I provided them for you here. I'm really mostly interested in what they allow you to do. Used to be I'd test them and have students remember each of them by name. But great, if you know its name and not how to use it, are you better off? No. I'm more interested in what they allow us to do. So I'm going to tell you their names today. I'm really just interested in what you remember you can do with them. So the first one, the first property we have is called the product of powers. And the product of powers states that when you are multiplying common bases, you add the exponents. So let's see that in action. That first one there, can we agree that those are common bases? They are both what?
Positive.
Not bases. They're both x's. So common bases basically tell us that you can add their exponents together if you are multiplying those bases together. So again, you don't necessarily have to show this in between step. This is just to serve as a visual reminder. But x to the power of 2 times x to the power of 3 is the same as x to the power of 5. So it makes that expression much more compact. Now, again, if you want to think of it on a deeper level, x to the power of 2, how many x's are being multiplied?
2.
2. X to the power of 3, how many x's are being multiplied? 3. In total, how many x's are being multiplied? 5. If you were to break it out long ways, you would see that there are a total of 5 x's being multiplied together, which is why the shortcut is just add their exponents together. It's a way to squish them together, so to speak. Now, second example brings back our little enemy there, the negative exponent. And I mentioned earlier, we don't like negative exponents. Is that correct? Yes. Here's the good news, though. only worry about negative exponents at the very end of your process, because sometimes in using these other steps, the negative exponent will take care of itself. So are these common bases?
No. Yes.
Yes. So the exponents, sure, they're different. One's positive, one's negative, but the bases are the same. So that allows me, since I'm multiplying them together, to add the exponents together. So 12 plus a negative 5 is going to give me a positive 7. And in that process, I don't have to worry about the negative exponent anymore, because as it got combined, as the two bases came together, the 12 plus the negative 5 balanced itself out and it turned positive, so that I'm happy. So negative exponents should catch your eye, but you shouldn't worry about them until you've kind of combined everything else in the problem. Sometimes they work themselves out. Sometimes they do not. So on this next one, common bases again. So we have n to the power of negative 4 times n to the power of 2. Because those common bases are being multiplied, we would add their exponents together. Negative 4 plus 2 is going to give me a negative 2. And then I grumble a little bit and say, ugh, I really don't like negative exponents. But thankfully, if I imagine this as a fraction, and I move this base with its exponent to the other side, I can rewrite this as 1 over n to the power of positive 2. So these two examples side by side show you that sometimes the negative exponents will sort themselves out. Sometimes they do not. If they don't, do that quick maneuver we did earlier, make that exponent positive, and you're good. Last one here, just to kind of, sorry, I saw someone pop up real quick. Did anyone have a question?
Sorry. So that 1 moves up?
So good question. Technically not. Technically what's happening here behind the scenes, I could rewrite this earlier step as 1 times n to the negative 2nd over 1, because there's 1's hiding everywhere. When that moves to the bottom, technically this then becomes 1 over 1 times n to the 2nd. But for our purposes, I got that was not useful. Of course, I don't. Oh, there it goes. There. All right.
That makes sense.
Yeah. So if you watch the animation real quick, technically the 1's along the way just hide. They were there all along. They just, oops, too much hidden, hide in that process. So yeah, a lot of times students think, oh, the 1's going to the top. Technically not. There's a 1 already there on the top, and then the 1 on the bottom just hides again. So good question.
The second one, the A7.
So you ready for the last one here?
No.
Oh, the second one, sorry.
Yeah, A7. Okay.
Yep, a to the 7th.
Just like okay.
So in the last one here, this process works no matter how many common bases you have. So you'll notice here, there's actually 3 different sets. So again, I'm going to show you the extra step that I like to put in there just to make sure I don't miss anything. It's not required, but it is possibly a good idea. So on this last one, I see, like I said, 3 sets of common bases. I have base A. Everything's being multiplied together. So the base A to the 2nd plus the -1 for the second base A. And if you like, if you're a color-coded person like me, that would be those pieces. Then I have base B. So I could think of that as B to the power of 3 plus 3. And then I have the C's, which is C to the power of what?
6.
Well, 5
5
plus 1, because if you recall, I said every base has an exponent, and if you don't see its exponent, that means that there's a 1 hiding there. So a lot of times that 1 gets overlooked in this process. Be careful not to make that mistake. So as I go through to clean this up a little bit, a to the power of 2 plus a -1 will become a to the power of 1. I personally like to hide them. Then I have b to the power of 3 plus 3, which is b to the power of 6. And c to the power of 5 plus 1 gives me c to the power of 6. And just like that, I go from this big mess down to something significantly more compact.
Can you hold on so I can write that?
Yep. So quick summary, if you have bases that are the same being multiplied together, you can add their exponents to combine those bases. Now, what's opposite of multiplication?
Division,
Division. What's opposite of addition?
subtraction.
Subtraction. So it kind of makes sense that if you divide common bases, you would end up subtracting their exponents. And this is the one we need to be a bit more careful on, because we were kind of cavalier there with multiplication and addition, because technically order doesn't matter. Regardless of what order you multiply things or what order you add things, you'll still get the same result. That is not true for division and subtraction. Switch the order, you significantly impact your result. So we need to be a little bit more cautious here, because the order that we write out this process will affect our final outcome. So Jay's saying we need one of those papers. I can go ahead and see if Leah has a digital copy, and I can share that out in Google Classroom as well. So I can certainly do that. The only thing though is it is kind of written with a math brain in mind. So I see it as useful. Not everybody does. Sometimes if you're like other students, you kind of need to see these worked out in person. So, all right. So the second property we have here is called the quotient of powers. So the quotient of powers again tells us dividing common bases, we subtract their exponents. So in this case, can we all agree that those are common bases?
Yeah.
Yes.
Okay. So since they're common bases and they are being divided, that means I'm going to subtract their exponents. And notice it is the top one being divided by the bottom one, which means I take the top exponent minus the bottom exponent. Follow the same order. The order you do the division in is the same order you do the subtraction in. And in this case, we get x to the power of 3. Next one. Again, I see that negative exponent. I'm a little worried, but I don't worry about it until the very, very end, because maybe it sorts itself out. So in this case, I'm going to have x to the power of 3 minus a -2. The subtraction is because I'm dividing the common bases. And of course, the 2 is negative, but 3 minus a -2,
Becomes positive. Becomes 5.
yep, becomes positive 5. Unfortunately, though, it doesn't always work out in our favor, which is why we have this third example. Again, dividing common bases of y. Here, the exponents are going to subtract to be 6 minus 8. but 6 minus 8
-2.
gives me a -2. So yes, I've combined them. I've created a new problem of a negative exponent, but don't fret. We have that trick that we've been using where we take that base with the negative exponent and move it to the other side. So we end up getting 1 over y to the power of +2. Oops. And of course, last but not least, this still applies even if you have multiple unique sets of common bases. Just make sure you don't accidentally scramble the exponents. So again, organization is key here. So I have x to the power of 12 divided by x to the power of 3. Ooh, that's hideous, but we'll go with it. So I get x to the power of 12 minus 3. Then I have y to the 5th divided by y to the -2nd. So that is y to the power of 5 minus a -2. And then I have z to the 3rd divided by z to the 7th, which gives me z to the 3 minus 7. So again, yes, there's multiple ones, but so long as you kind of work them out, you know, separately from each other, you should be able to get them combined nicely. And as I clean this up here, x to the power of 12 minus 3 gives me x to the power of 9. Y to the power of 5 minus a -2 gives me y to the power of 7. And z to the power of 3 minus 7 gives me z to the power of -4. And then I realize I grumble a little bit. I still have a negative exponent. So I imagine this whole thing as a fraction. I only have to worry about the base that has the negative exponent, and I pull it to the bottom to get x to the power of 9, y to the power of 7 still left on top, but now that z to the power of 4 has moved down below. So
I moved everything on the bottom and left 1 up top, but I see what I did because it was -4 instead of all positives.
exactly. So yeah, you don't want to just flip everything. So I'm glad you shared that. Because if you were to flip everything, that 4 would become positive, but what would become of the exponents 9 and 7? If I move them to the bottom.
You wouldn't have a fraction anymore. It would be
Well, it
They
would be a
become
fraction,
negative.
but the positive exponent, sorry, Alexis, what'd you say?
They become negative.
Yeah, those positive exponents would switch to negative, and I'd actually create almost a bigger problem than what I started with. So good catch there, Jay. I'm glad you were able to catch that in that process. We only are concerned about moving the bases with the negative exponents. Everything else can just hang out where it was left. So quick summary of that section: multiplying common bases, add the exponents. Dividing common bases, subtract the exponents. And then we get to our last two. We have the power of a power property. We have the power of a product property. So we're going to start with the power of a power. And it states that when a base has more than one exponent, multiply the exponents together. So you'll notice we don't have common bases here now. We just have one base with multiple exponents. If that is the case, all you have to do is multiply the exponents. So what does this first one become?
Z to the 12th power.
Z to the 12th power. Oops. What about the second one?
Would it be X to the negative fourth power?
It would be x to the negative fourth. And then we grumble a little bit. We say, oh, we don't like negative exponents. But again, if I imagine this as a fraction, and I take the base that has the negative exponent, move it to the other side of that fraction, we can clean this up to something we like a little bit better. Next one, throwing a little bit of a curveball for you. What's happening here, or what's different? What do you see?
There's
How many bases do you see?
two.
2 bases. Are they all sharing multiple exponents?
No, because the parentheses is with the B.
The parentheses is with the b to the third to be exact. So what about that a to the second?
You leave it alone.
Leave it alone. A to the second only has the 1 base and it only has the 1 exponent. So a to the second remains the same. What about b to the third raised to the fourth?
B to the 12th power.
Becomes b to the 12th. And then, of course, the last one I went overboard. How many bases do you see?
1.
1. How many exponents does that 1 base have? 3. The process is still the same. Sometimes it helps to see it kind of in segments. I like to work from the inside out. So n to the power of 3 raised to the power of 5 becomes n to the power of 15. But n to the power of 15 raised to the power of 2 becomes n to the power of 30. So again, we're not really solving anything. We're just manipulating them so that if one of these days they get dropped into an equation, they're a little bit cleaner to work with. Our last one, power of a product. When you have multiple bases that share an exponent, distribute the exponent to all bases. So this is where the parentheses is going to actually start to play more of a role rather than just grouping things together. So for the example of the first one here, how many bases are inside that set of parentheses?
3.
There are 3, because remember, bases can be numbers or variables. So I'm going to share that exponent of 2 to the base 3. I'm going to share that exponent of 2 to the base x. And I'm going to share that exponent of 2 to base y. Now, is anything there jumping out at you? Anything you can
Don't
do?
you multiply them?
Multiply what?
The exponents.
No, we only multiply exponents together if there's more than one exponent on the same.
Again,
Well,
3 to the second probably.
okay. So Alexis, sorry, you said something as well. What did you say?
add them.
So maybe, except in order to add exponents together, what has to be true about the bases?
They have to multiply.
They have to, well, they are being multiplied, but they also have to be
The
the same.
same.
The same.
So since x and y are not common bases, I can't combine these any further. But Leanna did point out for me, I can actually evaluate 3 to the power of 2. What is 3 to the power of 2?
9.
9. It doesn't look like it changes much, but maybe it's a little bit more useful later. So Miranda, you're right there as well. You're right on it. Anytime you have a base that is a value, if it has an exponent, just go ahead and evaluate it out, whether it's on your calculator or by hand. But I can't combine any of those other bases because they're not common bases. I can't multiply their exponents because they are on separate bases. That's as far as I can take that one. What about the second? How many bases do you see there? 3, and they're all sharing the exponent 4. So we're going to distribute it in to where each base gets its own exponent of 4. So we'll get a to the power of 4, b to the power of 4, c to the power of 4. Can I combine these all because their exponents are the same? No, trick question. Doesn't matter if the exponents are the same, the bases would have to be the same. So this one is as far as it can go.
Hey, are you teaching still?
Mhm.
Sorry, sorry.
You're fine.
I just need help with my mouse.
All right, what about this third one? A little bit different. How many bases do you see inside the parentheses?
3.
3. What's different about some of these bases?
They're not the same.
Well, none of the
no,
bases are the
because you have
same.
X to the third power and Y to the fifth power.
So some of them have exponents other than 1. Because so far, all these other exponents inside the parentheses have been 1s, which have been hiding. But that's okay, because we actually just covered a property for if something like this happens. So you said there's 3 bases. So the base 4 is going to get that exponent of 2. X to the third is going to get its own exponent of 2. And y to the fifth is going to get its own exponent of 2.
Can you multiply the exponents?
Why can we multiply the exponents?
Distribution.
Sort of. If you recall the property right above, power of a power, if you have a base with more than one exponent, you can multiply those exponents together. So x to the power of 3 raised to the power of 2 would become x to the power of 6. And we get y to the power of 10. And while I'm at it, can I actually evaluate 4 to the power of 2?
Yes.
I would get 16. Can I combine anything any further?
No.
Nope. Every exponent has exactly, every base has exactly 1 exponent. No common bases, no negative exponents. I'm happy. Last one. How many bases are sharing the exponent?
4.
What about, I see 5 bases.
Well, because the 2's outside the parentheses, so the exponent doesn't belong to the 2.
So the 2 outside the parentheses, the coefficient of 2 outside the parentheses is not going to be affected. It's not sharing the exponent. Spot on. So it's along for the ride right now. Is that correct?
Yes.
So 2 is going to drop down. Everything else, however, so 3 is going to get an exponent of 2. A is going to get an exponent of 2. B to the power of 2 is going to get an exponent of 2. C to the power of 3 is going to get an exponent of 2. Now, we need to clean some things up. Multiply what, Leanna?
The 2 to the second power of 2, you can get a 4.
The b to the power of 2
Yeah.
to the power of 2? Okay.
You get b to the 4th power, and then you get c to the 6th power.
So b to the 4th, c to the 6th. So anytime a base has more than 1 exponent, multiply those exponents. What about the a to the 2nd?
No, it stays.
So bring it on down.
And then you can simplify the 3 to the 2nd power.
What is 3 to the 2nd power?
9.
9.
And then you can bring the 2.
Bring the 2 down. Is there anything more I can do here?
2 times 9.
What is 2 times 9?
18.
18. There you have it.
I wanted to do the 2 with multiplying 2, but I see why I don't, because it's not the parentheses. Got it.
You're talking about this 2 here,
Yeah.
and this exponent of 2 here.
Yes, sir.
Yep, you're spot on. If it's not part of the if it's not inside the parentheses, it's not sharing anything. In fact, if you notice, it was along for the ride until the very last step. All right. So we covered a lot of properties. The assignment today is going to feel strange because it doesn't feel like you're getting an answer per se, because you start with an expression, you end with an expression. But if I was to make a recommendation here, let me kind of go off script real quick. You know you've simplified an expression involving exponents if you accomplish these three things. If you can say yes to each of these three things. I think it's three things. We'll see. So every base has only one exponent. Each base only appears once. So what that basically means is no common bases remaining. And the last one is absolutely no negative exponents. If each of those three things are true, you've probably simplified it as much as you possibly can. So every base has only one exponent. Each base only appears once, so no more common bases. Because if you have common bases, if they're being multiplied, you add their exponents together. If they're being divided, you subtract their exponents. And then at the end of that, I would actually save the no negative exponents concern for the very, very, very end. Because as we saw, sometimes the negative exponents work themselves out. So don't worry about them until you know that they're still hanging on. At which point you do that little maneuver, make them positive, you're good to go.